Welcome, everyone. So I'd like to start with a brief introduction to Nvidia. A lot has happened since the early 1990s when we first introduced the graphics card, or the graphics processing unit, or GPU. We were all about gaming and visual computing back then. In fact, we're still very much involved and very proud of our gaming heritage. It's what keeps us extremely agile today and adaptable in this crazy world. It's also very creative and a lot of fun. This is Project Sol, the quest for graphic realism. And what I'm going to talk to you about today is how gaming has evolved into an integral part of successful AI deployment in industry, on the ground, in the air, and even in orbit around our planet. Everything you see here is rendered with GPU. RTX stands for ray tracing, physically following rays of light to make the virtual look photorealistic. So lighting, shading, adhering to the laws of physics. Okay, enough of that. I think we'll move it on to show him how it's really done. So we've actually spent decades perfecting visual computing for architecture, for movies, for games, for automotive. But I'm going to show you how we can also pull AI into these virtual realms to train actual robots, actual machines operating in our world, the natural world, but trained in an environment where it literally costs you nothing to shoot up the room. It costs you nothing to come up with all kinds of scenarios where there are no limits, where you can now generate the unknowns from pseudo-random numbers, where generative adversarial neural networks take over the creation. But no equations, I promise. So this is our headquarters in Santa Clara, California. We're no longer just a gaming company. Nvidia provides what's known as full stack expertise, so the chips, the processing, the interconnect or networking, the storage, the hardware and the software. We provide the core tech reshaping industry today, and we're world class, but it's backed by a multi-billion-dollar gaming or visual computing industry, fueled by the demand for perfection, not just by gamers, but by the world's top scientists and researchers worldwide. And we're growing fast. There's almost $21,000 now around the planet, but we're still mostly working safely from home. Voyager on the right there should complete this year, connecting to Endeavour. And over at the back is our newest data center. So Selene, which took over 15 kilometers of optical cables. And zooming in to one area in Selene, each of the gold boxes that you see comprise 16 of our latest gen Ampere GPUs and the CPU, the memory and the networking that we call DGX. Each DGX replaces 150 CPU servers, and prior to June this year, a configuration that we call SuperPod was the world's most efficient form of compute. We missed the top spot this year by something like 0.505 gigaflops per watt. But Ampere and Mellanox, the switches and the networking, feature in the rest of the top 15 of the world's most efficient compute. One of our goals is to increase the size of the problems that humanity can solve. And let's face it, there's some big problems out there. But let's take a trip back to the early 80s. Just let me make sure that, that the audio is switched off to this because it's horrendous. Phil Hume is my big brother. This is actually one of his first games. So 8-bit, as we remember it fondly, is very, very clunky, but very, very easy. Although computationally, back then, of course, it was high tech. Today, you know, we just smile and maybe wince at it. Today, this is the realm of multi-agent reinforcement learning. Now we train agents to become artificially intelligent agents in much higher resolution with much more choice and therefore much more complexity. In my brother's game, there were less than 10 actions, so up, down, left, right, jump. Here there are 300 possible actions in the mathematical action space. in the game of Starcraft, actually Starcraft 2, the real-time strategy game that was released over a decade ago. The agents learn visually by assessing each pixel on the screen. So assuming just a small screen size of 84 by 84 means over 100 million possible actions to take at any moment, which means massive computation and demands what we know as parallel programming and parallel processing. Luckily, that's exactly what GPUs were designed to do, because what you can do with pixels, you can do with bits, with noughts and ones. And we can only perform this kind of training today because we have GPUs. Today with 80 gigabytes of memory on board each. So you can basically SSH into the entire Selene data center, or just a superpod or a cluster of the DGXs, or just one DGX, or just one of the GPUs in the DGX, or even now just one instance of one GPU. And this kind of modularity and flexibility is why our GPUs can be found in every major cloud provider around the globe. And to help you tackle your most important scientific and big data challenges. And soon we'll have this. So combining our own CPU, Grace, DPU, data processing unit from Mellanox, and our next gen CPUs. And this is, of course, backed up by a very extensive collection of optimized software built on top of CUDA, our parallel programming language. These 60 plus libraries literally unleash the power of our GPUs. We've written the code for you, and we put it all in a central repo. A key component of the Nvidia AI ecosystem is the GPU catalog, or Nvidia GPU catalog, NGC. Currently, there's over 150 enterprise-grade containers, over 100 pre-trained models and industry-specific SDKs that can be deployed on-premise, in the cloud, or at the edge, to help you deliver business value faster. Every single asset is validated for performance, for quality and security by us. And each container contains all of the software you need to run out of the box. And of course, containers mean repeatable, shareable, and auditable. Code such as detecting people in streaming video, detecting vehicle types, and much more is available there for you. And if you're doing straight data science, then code like Rapids will accelerate it. I'd actually need about another hour to introduce you just to this library. So I'll have to leave you to investigate further via the website. But my role at Nvidia is global, actually beyond the planet, as I also cover anything connected to space. One of the first things that I did when I joined Nvidia, which was over 6 years ago now, was help them to form the Frontier Development Lab that works with space agencies like NASA and the European Space Agency to develop new tools to help solve some of the biggest challenges that humanity faces, like an extreme weather prediction tool that gives farmers around the world precious time to harvest before heavy rainfall arrives. Or much further afield, using ray tracing to render the irradiance field around craters at the moon's south pole, which lie permanently in shadow. This aids in the search for landing sites and the search for water on the moon, part of NASA's Viper lander mission, which will take place prior to astronauts landing. Or performing super resolution on imagery of the moon, either on the ground or actually onboard satellites themselves. So our embedded GPUs, which can literally just be credit card sized, are actually in orbit right now with partners who actually provide them with radiation tolerance. Here is an example from AI Tech of their space grade Venus with our TX2i, and there are many, many more that actually provide this capability. This is Orbital Sidekicks units, the aluminium box far right. Which actually sat external to the International Space Station, where it performed hyperspectral imaging for over 1 year. It's since been decommissioned, but they're about to launch their latest generation any day. Because this actually is the new goals. So this kind of imagery helps us prepare for climate change, helps us improve farming capability, optimizes shipping routes. There's actually hundreds of use cases of taking these multiple frequencies and channels of data. and providing, you know, much improvement. These two alternating images were, you know, collected by satellites from Planet, and they show part of the Bahamas after Hurricane Dorian hit in 2019. So this is essential for mapping and assessing damage and determining where to deploy aid. And we have thousands of satellites in orbit. You know, society does, bringing us much more data than we can currently handle, unless you have a GPU accelerated parallel processing. But real-time Earth observation, so, you know, from satellite imagery, is now on every government's agenda, and we can provide both that modeling and visualization capability. So this demo, hopefully it will run smoothly and not clunkily, which it sometimes does through Zoom. It shows the capability of what we mean by simulating the science. So this demo fuses our platform called Omniverse with rendering and our physics engine, software called Index and NanoVDB with ECMWF, so that's the European Weather Centre data. This kind of visualization allows not just scientists, but business execs, policymakers, and the general public to use the information and take action. These simulations are not just photorealistic, but they're physically accurate models in a collaborative platform where anyone on the planet can actually work together. And Nvidia already has the platforms for all kinds of climate action, so monitoring the environment, helping with smart grids and energy efficiency, weather and climate forecasting and planning for response to harmful events. But this tech will truly help save the planet. So CloudXR is a powerful edge computing platform for extended reality. It's built on RTX to deliver virtual reality, augmented reality across 5G and Wi-Fi networks. So think meetings with avatars, you know, developing new capabilities for smart cities, security systems, retail intelligence, industrial automation, and here, you know, CAD, computer-aided design for cars. So basically you put on a headset and you enter the actual environment, you know, like Dave and Sean are there. They can talk to each other, they can move around, you can manipulate the design, because this is a fully immersive environment. You put on gloves and have full haptic you know, touch capability. So it's a new way to, you know, perhaps provide interactive training or just meetings. So I'd like to just pivot slightly here and talk about the, you know, the actual how. Building an AI product is about training and inference, or, you know, inferring from new data. So we provide the data, or you can create it in a simulated environment first. You perform machine learning, you validate and test, and then you deploy the actual model. DGX handles the training. Jetson, or you know, our embedded products for, e.g., robotic inference, or EGX for edge compute, takes on with the actual inference side of it. And I mentioned our central repo earlier, NGC, but just one of those libraries is TRT. TensorRT, which automatically speeds up the inference as fast as physically possible. We've actually made all the optimizations for you. So here's a basic algorithm, a recipe for success. Defining your objective, or what the AI system will actually do, is key. But I want to focus, unfortunately, only have time to focus on step 5. So creating that sandbox virtual environment. And of course, getting good parallel programming coders is essential too, but even ninja brains have limitations, while AI, so machine learning or deep learning, extends those limits, you know, exponentially. And this is even more apparent in an environment where the limits are endless. In fact, you're only bounded by the compute that you have available, because the real power of virtual worlds is teaching in parallel. And this work is now 3 years old with Carnegie Mellon on distributed reinforcement learning. Powered by just a single GPU, actually a Volta previous gen GPU, you're able to train thousands of agents at once. And we can even use AI. Just let me click this video and perhaps drop that and move it on a little bit. What we can do is we can even use AI to take a 2D photo and generate 3D images with no modeling required. Generative adversarial neural networks literally create from scratch. We call this GANverse, GANverse 3D, and actually just demoed it at SIGGRAPH. So do take a look at that in a little bit more depth if you can. Nothing is actually more powerful than humans augmented with AI, but we'll also never have successful AI without humans in the loop for mission critical automation. If you're deciding who to tag in a photo, for example, then go ahead, fully automate, but otherwise human in the loop is essential. So you should harness virtual worlds, and that's why we're connecting the physical and virtual worlds. Once you've trained to perfection, you simply transfer to real for faster time to production, allowing verified, validated prototypes to actually exist before they're even built. Training that requires masses of data can be generated at negligible cost within the virtual world as training happens. It's actually child's play to conjure up all manner of corner cases that are extremely difficult to provide in the real world, either infrequent, they don't happen enough, or they're literally too dangerous. The unknown unknowns can finally be realized in the virtual world of infinite possibilities. So the AI system becomes truly more experienced than we ever could be. This is known as domain randomization, and it's actually very important for robust AI systems. For example, here in a fulfillment center. So this is the concept of digital twinning. Fulfillment centers receive, store, pick objects, pack objects, and then distribute them. But synthesizing data is essential today. So it's key in dealing with privacy issues, reducing bias. In Omniverse, you can rapidly spawn new versions of objects and environments with different colors, lighting, materials, and poses. And, as is shown here, digitally twin anything. So, for example, with robotics, here with the a virtual animal robot, you can train the robot with reinforcement learning, to do whatever task you want it to do, here climbing up the stairs. But then all you have to do is simply transfer the policy to the real world. So here, taking what you've learned and putting it into an actual animal robot, and have it climb actual steps or up actual steps. But the really fascinating thing is that in Omniverse, you can build anything. This isn't a photograph. This is a screenshot from BMW's factory twin of their production facility in all this, exquisite detail. With Omniverse, on the left here, collaborators can work on separate machines across several applications. They're each composing their part of the scene, whether it's modeling props or building the environment, textures, lighting. And each are connected to the core, to nucleus, where the AI happens, and the rendering, the physics. Like GitHub, each user is simply passing and receiving the deltas of changes, so they can actually see them occurring in real time. And some of the applications included in Omniverse, either built by us or by the community, I'll just highlight a couple, such as audio to face. So this lets you record and play back vocal audio. I don't think the audio is actually running through Zoom for some reason, but it basically gives immediate animation and transferring generated motion onto any kind of custom faces. Machinima pulls in all of our gaming goodness for truly accurate physical simulation with PhysX, Flow, and Blast. We work with partners like Wrench on here, AI pose estimation. And of course, it includes the RTX renderer itself, and that's a scene from Marvels, which we then made into a competition, and the community actually sent in, their own versions. It's quite cool if you look online. But basically, we're not just playing games, of course. This is BMW's STR, or Smart Transport Robot. It's capable of a 1,000-kilogram payload, and it's fully autonomous, running solely on Jetson Xavier, and designed entirely in Isaac in Omniverse. But basically, it adheres to all of BMW's safety standards. We do a lot of work across AV or autonomous vehicles in safety and redundancy. And just to give you an example of the complexity that we go to when we talk about physically accurate simulation. This collaborative research just won Best Student Paper at RSS Robotics conference. The simulator actually predicts the forces acting on a knife as it presses and slices through, in this case, an apple. You can actually see the springs in cyan between the cut elements of the actual mesh, weakening as the knife exerts contact forces. This is essential work for robotic surgical assistance too. But unfortunately, I don't have enough time to really get into this in depth, but you only need an RTX GPU to use Omniverse. And we have tons of resources and 100 tutorials actually online to actually teach you a lot more. There's also lots of work that we've done with natural language processing, with conversational AI too, but I am unfortunately out of time. So I can only pass these resources on to you, and let me know if you need anything else. The best way to get started is with our embedded GPU. So please check out my colleague Wei Xiao's talk and the many resources that we have online. Also, my colleague Kate is giving the keynote. Developer kits only starts at actually less than $100. And for academia, we also provide free teaching kits, and students can actually train to give our online classes at no charge. So the Deep Learning Institute curriculum actually spans from fundamentals to industry-specific applications, teaching you how to build and deploy neural networks for a variety of tasks, whether you're just beginning your journey or not. For startups using our tech, please sign up to Inception, where you'll get a lot more support, and that includes the access to VC, to venture capital in the VC Alliance. So please don't hesitate to contact me with any further questions, and thank you so much for listening. I do hope that this has been really helpful. Thanks very much.